Welcome to the last part of this tutorial, which is a general discussion on the DVAE class of models, in which we will try to present the outcomes of our DVAE tool and the research challenges that remain for their development and their use in the future. So, first, we will recall the fundamental motivation for developing and using DVAEs. We recall that the goal is to mix the world of dynamical models, aiming to model the dynamics of sequential data, and the world of VAEs, aiming to model the latent factors of data variations. By doing so, we expect to separate the data dynamics from the other factors of variations and use the latter to augment the expressivity of the models. Another way to express this idea is to point out the superiority of DVAEs over RNNs. Here we think the simplest way is to directly cite a paragraph from the VRNN paper by Chung and colleagues. This paragraph summarizes the general idea in a very efficient manner. We show that the introduction of latent random variables can provide significant improvements in modeling highly structured sequences such as natural speech sequences. We empirically show that the inclusion of randomness into high-level latent space can enable the VRNN to model natural speech sequences with a simple Gaussian distribution as the output function. However, the standard RNN model using the same output function fails to generate reasonable samples. An RNN-based model using more powerful output functions such as the GMM can generate much better samples, but they contain a large amount of high-frequency noise compared to samples generated by the VRNN-based models. Similarly, we can point out the superiority of DVAEs over classical non-deep dynamical Bayesian networks and state space models. Again, let us directly cite an excellent paragraph from the VRNN paper. Drawing inspiration from simpler dynamic Bayesian networks, such as HMMs and Kalman filters, the VRNN explicitly models the dependencies between latent random variables across subsequent time steps. However, unlike these simpler DBN models, the VRNN retains the flexibility to model highly nonlinear dynamics. Of course, this kind of statement applies to the whole DVAE family of models, not only to VRNN. Now, we really would like to insist on a very interesting features of the DVAE models, which is their flexibility. Let us first rapidly recall the flexibility of the generative model. We have seen many different generative models that can be derived from the general chain rule by simplifying the variable dependencies with conditional independence assumptions. Those simplifications are summarized in this table for the models that we have detailed in this tutorial, or at least we have mentioned as iconic examples of the DVAE models. When simplifying the variable dependencies, in other words, when designing the generative model, complexity issues may be considered. To illustrate this important point, we can directly cite a paragraph from the Storn paper by Bayer and Ossendorfer. We can restrict ourselves to prior distributions over the latent variables that factorize over time steps. This is much easier to handle in practice, as calculating necessary quantities such as the Kullback-Leibler divergence can be done independently over all time steps and components of ZT. But at the same time, the systematic aspect of the VAE methodology and the versatility of current deep learning toolkits enables in principle to train a model of arbitrary complexity. So we can be prone to increase the complexity. And for example, in this framework, it is very easy to go not only from a linear dynamical model to a nonlinear one, but also from a first order temporal model to a much higher order. Next, we can point out the flexibility of the inference model. We can recall that the design of the generative models implies consistency constraints on the inference model, something that has been disregarded in several seminal papers on DVAEs. Even though the exact posterior distribution is analytically intractable in DVAEs, the deseparation principle allows us to analyze the structure of the exact posterior induced by the chosen generative model And we recall that it seems quite natural to exploit this knowledge to design the structure of the inference model, even if it's not mandatory. For example, one may drop possible non-causal dependencies for the purpose of online applications. Also, the sampling procedure to compute the VLB in DVAEs has to be recursive due to the dynamical nature of the model, a constraint that standard VAEs do not have. Finally, we would like to insist again on the flexibility of the implementation. We recall that one given probabilistic graphical model, indicating dependencies between random variables, can have multiple implementations. And we believe that when describing a DVA model, it is important to explicit both its compact representation and its developed representation in terms of graphs and equations. We have here an example of compact representation in the figure on the left, and a developed representation in the figure in the middle and on the right. We can see that the same compact form have here two different implementations, one where the RNN internal state is shared by the two generative distributions of ZT and XT, and one where we have a different internal state for each of these distributions. The chosen implementation can, of course, significantly influence the modeling performance. The next point is that in this tutorial, we have clearly focused on models based on RNNs that are based on an infinite order temporal modeling. And of course, we have seen that in DVAEs, RNNs are possibly combined with feed-forward fully connected networks. And it is clear that other network architectures can be considered for sequential data modeling. We will not detail such architectures, but we can at least say a few words. First, convolutional neural networks can also deal with sequential data of arbitrary length using finite order temporal modeling. And temporal convolutional networks are getting more and more popular due to competitive performance with RNNs, while being more flexible and computationally efficient. See, for instance, this paper by Liu and Mesgarani for an application in speech separation, or this paper by Richter and colleague for a VAE-based speech enhancement method. And finally, we can mention the family of transformer models that are based on attention models that efficiently learn the interdependencies of vectors in a sequence or between two sequences without recursive process. Transformer models are state-of-the-art in natural language processing with discrete random variables and are getting more and more popular for modeling real-valued signals in signal processing applications. We can mention a very interesting example of joint modeling of a discrete value observation sequence and a continuous valued latent sequence with a transformer VAE with application to music score modeling in this paper by Jiang and colleagues. The next point that we would like to address here, which is a very important point, is the issue of latent factors disentanglement. We have not insisted much on this point so far in this tutorial, but one of the original goals of the VAE is to provide a so-called disentangled low-dimensional representation of the observed data. And as stated in this paper by Chen and colleagues, a key goal of representation learning is to identify and disentangle the underlying causal factors of the data so that it becomes easier to understand the data, to classify it, or to perform other tasks. And a VAE or a DVAE mixes stochastic unsupervised representation learning with a deterministic temporal encoding-decoding model. And in some part of the literature on models that encode an observed vector sequence into a single latent vector, there is a general warning. If the deterministic temporal model is too powerful, for example, an autoregressive model, it can have a tendency to capture all data information without the latent variables being actually used. And this is something that is clearly discussed in this very interesting paper by Chen and colleagues. And it is also reported in the literature on text processing and natural language processing. We recall that there are a lot of papers in NLP that combine RNN with a single latent vector VAE. And of course, solutions have been proposed to address this problem, but it seems like there is not yet a consensual manner to solve this issue. And in DVAEs, The disentanglement challenge is to separate the data dynamics, that is, their temporal structure, from other factors of variation. For example, the speaker identity for speech data. And we recall that we focused on models with a sequence of latent vectors, and not only one single vector associated with an observed data sequence. And thus, addressing the disentanglement challenge takes a new flavor compared to static VAEs, since the causal factors of variation can have their own dynamics. So one way to address this challenge is to apply hierarchical modeling to the latent factors, but on the time dimension. For example, we have seen that the disentangled sequential autoencoder of Lee-Mant includes a latent variable defined at the sequence level in addition to the frame level variable ZT. And for speech signals modeling, this appears as a promising way to separate the speech signal content and the modeling and control of the speaker information or the session information, which are defined at the sequence level. If we go a bit further in this direction, we can here mention another very interesting model that is called factorized hierarchical VAE. In fact, we already rapidly mentioned this model at the end of part 2, but we did not present it in details because it is a bit more complicated than the other models. And the interesting point here is that FHVAE learns to encode local attributes, such as the phonetic content of a speech signal, into a local segment-level variable Z1, and it learns to encode global attributes, such as speaker gender, into a sequence-level variable Z2. And the authors of the FHVAE paper provide a series of very interesting experimental results where they analyze two different sentences produced by a male and a female speaker, and then they generate hybrid sentences by swapping the values of one of the two latent variables before resynthesis. For example, we can see here that they combine variable Z2 from the top left sentence, which is assumed to encode the female gender, with variable Z1 from the bottom left sentence, which is assumed to encode the phonetic content of this sentence that was produced by a male speaker. And the result of the resynthesized sentence is the phonetic content of the second sentence produced by the female voice. So this is a very nice example of successful disentanglement and manipulation of speech attributes. Finally, what we can conclude here is that, in a general manner, the issue of separating dynamics from other factors of variation is still largely open in the literature of DVA models with a sequence of latent vectors. You have certainly remarked that we love to cite literally the content of DVA papers, so let's do it one more time. It is interesting to see that in the FHVAE paper that was published in 2017, the authors say, to the best of our knowledge, there has not been any attempt to learn disentangled and interpretable representations without supervision from sequential data. And about SRNN, VRNN, and the structured VAE model of Johnson and colleagues that we rapidly mentioned at the end of part 2, Su and colleagues also say, it remains unclear whether independent attributes are disentangled in the latent space. Moreover, the learned latent variables in these models are not interpretable without manually inspecting or using labeled data. So, in conclusion, we may say that at the deep learning era, things go so fast that 2017 is already a long time ago. But we feel like it is not so old, because we did not find much more recent elements in the literature on this disentanglement problem in the general DVAE framework. Again, for the family of models that consider a sequence of latent vectors. So we may conclude that Stone, VRNN, SRNN, etc., and in a more general manner, the DVAE class of models provide an elegant and powerful mathematical and methodological framework for sequential data representation learning, but it seems that there is still a lot of work to do on the disentanglement challenge. And solutions for the disentanglement of ZT, inspired by existing structure or hierarchical static models, still have to be developed. Okay, this concludes our tutorial. Thank you for your attention. We hope that you enjoyed this tour in the world of DVAEs. Before we move to the question session, we would like to recall that all resources that were presented in this tutorial are available in this GitHub repository. You will find there our DVAE overview paper that is also available on archive. You will find the slides of this tutorial. And very importantly, you will find the PyTorch implementation of several of the DVAE models that we have presented in the tutorial. This implementation was made by Xiaoyu Bi, our PhD student at INRIA Grenoble, and we can thank him warmly for this great work. And finally, you will find a Google Colab notebook that will enable you to play with these models on speech signals. Thank you again, and see you at the question session.